时间到已经啊 ，OK。So the next speaker today is by Professor Liu Xing from East China Normal University. He will talk about sharp bond on the abelian automorphism groups of surface of genotype. Please.
Okay, thanks for the introduction, and thanks also to the organizers for the invitation. It's my honor to give a talk here. Before starting my talk, I would also like to apologize for the inconvenience in arranging my talk. Because of the COVID-19, the city Shanghai suddenly shut down in this March. Okay, fortunately, the situation becomes much better now, and I can get what I need to prepare my talk. Today I will talk about the up bundle and the abelian automorphism groups of surfaces of general type. This is a joint work with Professor Cindy Tang. Let's start with the Q case. We are mainly concerned about the up bound of the size of the automorphism groups. So the varieties we consider will be of general type. So in the Q case, we will consider the Q is of genus G at least 2. And we will work always over the complex number. So in the 19th century, Horowitz already get the up bound for the total automorphism group of C. That is the size of the total automorphism group is bounded from above by 184 times G minus 1. But for the abelian subgroup and also the cyclic subgroup, the size of the subgroup was obtained in much later. This is obtained by McLaughlin and Harvard, and the up bound is given by, for the abelian group, the up bound is given by 4G plus 4, and the cyclic subgroup is given by 4G plus 2, and these two bundles are much smaller than the up bound for the total automorphism group. And also we know that this three up bundles are sharp. I mean, there are examples of Qs which admit an automorphism group reaching this three up bound. And also we have some calculations for the equality. So for the first equality holds if and only if the QC admit and Galois cover to the projective line, which has exactly 3 branch points, and the ramification index should be 2, 3, and 7. And for the second equality, if the Q admit an abelian automorphism group of size 4G plus 4, then the Q should be isomorphic to this hyperelliptic curve, or it is the Fermat's force curve. Of course, in the latter case, the QC has genus G equal to 3, and in the cyclical automorphism case, the last one, if the equality holds, then the QC should be isomorphic to this hyperelliptic curve. Here I should emphasize the second case. I mean, the general case is that the Q reaching the up bound is a hyperelliptic curve. Here, the genus G can be arbitrary. But when G is small, that is when G is equal to 3, there are 2 types of Q which attain the maximum order. That is, the first one is the usual hyperelliptic curve given by y square equal to x of power 8 plus 1. And the other one is given by this Fermat's force curve. And this Fermat's force curve is of course not hyperelliptic. is not hyperelliptic. Yeah, such a phenomenon happens also in the surface case, as we will see later. Okay, so now let's go to the automorphic group of surface. So let S be a minimal smooth projective surface of general type. And here Ks is its canonical divisor. Here we want to get an upper bound for the size of the automorphic group of S, which is given by some function in this the self-intersection number of Ks. Okay, the self-intersection number of Ks is also called the Foster number of S. The first result was given by Ajot in 1915. He proved that the automorphic group of S is finite, and he gives an upper bound which is an exponential function in Ks square. And later there are many improvements here. I just mentioned two of them. This is given by Howard Sums and Hochberg Zorn. They give some polynomial bound for this automorphic group. Finally, it was given by Gang Xiao that the automorphic group of a surface of general type is linearly bounded by the Ks squared, the self-intersection number. And the bound given by Gang Xiao is also sharp here. That is, he also gave a characterization of the equality. So if S admit an automorphic group of maximal order, then the surface S should be somehow is C times C, the self product of QC. Here C is a Horowitz curve. Here by Horowitz curve we just mean that C is an algebraic curve which admit automorphic group of maximal order, that is this one. When the QC has a maximal order of automorphic group. And here G lot is some norm subgroup acting freely on C times C. So the surface S is almost C times C, but maybe there's some norm subgroup act on this C times C. Yeah. So the question for the total automorphic group is solved by Tan Xiao. Now we turn to the abelian subgroup. So let G be an abelian subgroup in the total automorphic group of S. And we also want to bound the size of G from above by some function in Ks square. Yeah, in the Q case, we already know that in the Q case, we already know that the upper bound for the abelian subgroup is much smaller than the bound for the total automorphic group. So in the surface case, we also we also expect an upper bound which is much smaller than the bound for the total automorphic group. Yeah, first, Howard and Samson got in 1982 and quadratical bound for this abelian subgroup. That is, and the upper bound is quadratic function in Ks square. And later, Gang Xiao first obtained a linear bound. He proved that the size of an abelian subgroup is bounded from above by 15.2 times Ks square plus 13.2 if Ks square is at least 114. As pointed out by Gang Xiao in his paper, this bound is far from being sharp. That is, he expected he was expected a bit bound. So This is so after that there's some improvement for this up bound. Here Jinxin Cai improved this up bound in 1998. He proved that the up bound of G is was improved into 13 times Ks squared plus 24 if the Euler characteristic of the structure shift is at least 315. Okay. Although we are mainly concerned about the abelian automorphism group of surface case, we would also like to mention the result in high dimension. So let X be an manifold of general type. Many mathematicians worked on this problem and made some progress in some cases. Here, for example, Howard Sampson and Zambo and Deqi Zhang proved variance polynomial bound for this total automorphic group. And the linear bound was first obtained for abelian subgroup by Jinxin Cai and Gang Xiao. They proved a linear upbound for abelian subgroups. Here, Jinxin Cai proved for the case when n equal to 3, and Gang Xiao proved for n. And finally, it was proved by Heiken, McConnell, and Xu, a linear bound for the total automorphic group of X for any dimension. Okay. So now we come back to the case, to the surface case. So let G here is an abelian subgroup. As we mentioned before, Gang Xiao and Jinxin Cai proved obtained a linear upbound for this subgroup. But yeah, as they point out in their paper, the bound obtained by them is far from being sharp. Yeah. To get the sharp bound for the abelian subgroup, people first try to take some special cases as a test. Yeah, one such successful attempt is the fibered surface case. So suppose that S admits fibration. So here F is a fibration from S to a QC, whose general fiber is Q of gens G at least 2. And in this case, we consider the subgroup which keep the fibration F invariant. That is, an automorphism is said to be in the automorphism of the fibration F if there exists an automorphism tau in the auto C, such that we have the following commutative diagram. So sigma is an automorphism for S, and here the sigma induce an automorphism on C with this diagram. That is, this automorphism should keep the fibration F invariant. And because here any automorphism in this auto F keep the fibration F invariant, so we have an exact sequence for this subgroup. That is the auto F. Here, lot F is the subgroup which keeps every fiber invariant. That is, keep for every fiber, it maps to itself. For an automorphism in auto F, it just keeps the fibration invariant. It maps this fiber to another fiber. Yeah, and this causal Q can be valued as a subgroup in auto C. This is the set of tau here. So so somehow from this exact sequence, one can decompose the automorphic group of the fiber ratio into two parts. One is the subgroup which keep the general fiber of F invariant. So this can be valued as a subgroup of the automorphic group of the general fiber. So this is a subgroup of an automorphic group of a Q. And also the causal Q can be valued as a subgroup of auto C. So Q is also a subgroup in the automorphic group of an edge break Q. So this somehow decrease the dimension. I mean, the problem is about the automorphic group on a surface S, but from based on this exact sequence, one might decompose this group into two parts, and the two part is about the automorphic group of edge break Q. So this is maybe one reason for that many mathematicians make progress in this case. Okay, so let's mention some progress in this direction. So here I just note GF is a subgroup of auto F. So if I'm writing this way, it just means that there exists a fiber ratio on S. So we have already a fiber ratio on S. Here F has to see the fiber ratio. And just write G is a linear subgroup of auto S. So here in this case, as this surface S mate has no fiber ratio. Okay. So in this lecture, Zhijie Chen first proved a result in the case when the genus of the fiber equal to 2. He proved that the upper bound of GF is given by 20.5 times Ks squared plus 100. And if moreover, this group is cyclical, then the upper bound can be given by 20.5 times Ks squared plus 19. Based on this result for fiber surface, Zhijie Chen was able to prove the result on the linear subgroup of S. So if S admits a pencil of gens G equal to 2, and Ks square is not equal to 1, that is, Ks square is at least 2, then this bound holds for any abelian subgroup. That is, the abelian subgroup, the bound for the abelian subgroup is given by 20.5 times K squared plus 100, and this is for the cyclical case. Here, I would like to mention that if Ks squared is at least 8, and S admits a pencil of gens G equal to 2, then S admits exactly one, S admits a unique pencil of gens G equal to 2, and then you can get the net result directly from this one, because there is a unique pencil of gens G equal to 2. Then for any automorphic group, it should keep this pencil invariant. But if K square is small, that is, it's smaller than 8, then there might be more than one pencil of gens G equal to 2. Yeah. And
Liu Xing, sorry to interrupt you. So yeah, the pencil may have a base log. So
yes,
is okay.
If K square is smaller, then the pencil might have a base point.
Then if you blew up base log, then Kx is not minimal, then your early result, you assume S minimal, right? So
yes, yeah. For the if you want to bound the up bound for this abelian subgroup, we always assume this here S is minimal, because if S is not minimal, then K square might be negative. So we always assume S is minimal. Here, if S if is I'm sorry, here if the pencil has a base point, then we have to blow up this base point and get a vibration on this regulated by S theta, and then we will use the result on this fiber surface case. And here, okay, I'm sorry, here. In the fiber surface case, here we just require this vibration is relatively minimal, and S is not necessarily to be minimal. We just require this vibration is relatively minimal.
Oh, I see. Thanks. Yeah.
Yeah. When we consider the bound for the surface, then S should be minimal. And for this fiber surface case, we just require S is relatively minimal. Okay. Yeah. And also, Zhijie Chen's result is sharp. That is, he constructed an example to show these two bounds are sharp. Yeah, they are example which obtain this, the example of surface which admit an AGEA subgroup reaching this up boundary. Yeah. Okay. And later, Jinxin Cai considered this question for the case when the genus of general fiber is equal to 3 or 4. And in this case, Jinxin Cai proved an up bound for the AGEA subgroup of the automorphic group of the vibration. So GF is bounded above by 20 KS square plus 19.6. And based on this result, he was able to prove that for any surface of general type whose invariant satisfy this inequalities, then the AGEA subgroup is bounded from above by 20.5 times KS square plus 100. Here, the reason is that when the invariant of S satisfy this inequalities, then there must be there exists a pencil on this surface S who is the genus of its general fiber is equal to 2, 3, or 4. So Jinxin Cai can got this result, and because the KS square is at least is not small, so such a pencil should be unique, and there is no base point. Yeah. Okay. After this, two results. I mean the Zhijie Chen's result and Jinxin Cai's result. And general conjecture is that this bound should hold in for any surface of general type if the invariant of S is not small. So this is a general conjecture. Okay, now we come to our main result. Our first main result is just check this conjecture, and we prove the following. So let S be a minimum surface of general type whose geometric genus here, geometric genus is just this number. If its geometric genus is at least 6, and G is an AGEA subgroup, then we have this this bound. And moreover, if any of the above equality holds, then the surface S has a vibration F has a vibration to the projective line of gens G equal to 2, and also the KS square should be equal to 2PG minus 4. This is the minimum possible for this KS square. This is given by the not inequality. The Ks square is at least this number. Here, Ks square must be equal to this number if the equality hold. Okay. So this is our result for this for the up boundary of the abelian subgroups. Okay. We will also construct examples to show that this up boundary is sharp. That is, we construct a series of surface S which obtain this up boundary. That is, for any integer, any at least two, there exists a surface S whose geometric genus is equal to 4n plus 2, and k square is equal to 8 times n. And there exists an abelian subgroup G on this surface S whose size is equal to 20.5 k square plus 100. And also we can construct another example with a cyclic subgroup which obtain the maximum possible. so the bound obtained in our theorem is sharp. And also we construct two examples which shows that our assumption here, we assume that the geometric genus should be at least 6. These two examples will show that this assumption cannot be dropped. I mean, the first example is this one. This is the equation of this S can be written down explicitly. Here, S is just the surface given by z square equal to 18th of power 8, x of power 8 plus y of power 8 plus 1. This is just you can visualize S is a double cover of P2 branched over the Fermat's 18th cube. Yeah. So, by direct computation, we know that the geometric genus of S is equal to 3 and K square is equal to 2. And on this surface, there exists an abelian subgroup of size is equal to, here 2 times 8 times 8 is equal to 128, which is strictly larger this number, which is strictly larger than 20.5 times K square plus 100. Here, because K square is equal to 2, so this number is 125. So this is strictly bigger than this one. This is an example with the PG is equal to 3. And also, similarly, we can construct this example. This is similar. This is the surface S is just a double cover of P2, whose branch locus is the Fermat's 10th cube. Yeah, this cube. And also, you can compute the invariant of S. The geometric genus is equal to 6, and K square is equal to 8. And also, there exists an abelian automorphic group whose size is equal to 200. This is 2 times 10 times 10. And this number is just equal to this number, 20.5 times K square plus 100. This is this satisfies this inequality. It's equal this equality, but there exists no fibration of gens 2 on S. Yeah. On this surface, there's no such fibration. This is when. Yeah, here our result is that if this geometric genus is at least 6, then the equality holds. We should have this property on S, that is S should be admit fibration of gens G equal to 2. But for this example, there's no such fibration. Okay, yeah, this is this two example shows that this assumption cannot be dropped. And also, this is can be valid as a similar result for the Q case. Yeah, as we said before that, in the Q case, when the abelian subgroup reach this up bound, this Q should be of this should be this hyperelliptical. But in the when the genus G is small, that is when G is equal to 3, then there exists another example which attain this maximum order. But in the Q case, we don't have a exceptional case for that. The size of the abelian group has a uniform bound. But in the surface case, we do not have such a uniform bound. When PG is large, is a uniform bound by this number. But when PG is small, we have a counter example which is larger than this number. Yeah. Okay. And this is our main result for this for the bound for the size of abelian subgroup. And to prove this result, we will also need to consider the fiber surface case. So on second result is about about such questions in the fiber surface case. So let here Fs to C is be a relative minimum fibration, and whose general fiber is of genus G at least 2, and here GF is an abelian subgroup. And suppose that the base QC is isomorphic to P1, isomorphic to the just the base Q is the project line, and we assume that the fibration F admits at least 3 singular fibers. Then we have the following bound for this for the size of this abelian subgroup GF. That is, GF is bounded from above by this by the maximum number of these two numbers, and also this maximum number is less than this number. The latter inequality is just given by the so-called slope inequality. Yeah. So the bound of the up bound of this abelian subgroup is given by this number. This is 2g plus 1 square over g times g minus 1 times kf square. Here, kf square and EF is just the relative invariance for this fibration F. So in our case, when the base QC is isomorphic to P1, then Kf square is equal to Ks square plus 18 times G minus 1. And EF is just the Euler characteristic of S, the topological Euler characteristic of S plus 4 times G minus 1. Here we should emphasize that in this theorem, we do not require S is of general type. We just require that S admits at least 3 singular fibers. S can be, S is not listener of general type. And also here, if the size of this abelian subgroup is the maximum possible, that is when GF is equal to this number, then F must be hyperelliptic. This is just because of the slope inequality, because this inequality is just from the slope inequality. So if this is equal, then this should be an equality, and F should be hyperelliptic. Yeah. And here, when G is equal to 2 is just our result on this theorem, on the first theorem. That is, you see that when G is equal to 2, this is just 2 times 2 plus 1 is just 25, and here is 2. So it's just 12.5 times Kf square. And Kf square when G is equal to 2 is just Ks square plus 8. So it's just this number, 20.5 Ks square plus 100. So when G is equal to 2 is just our result in this in the first theorem. That is the upper bound for this abelian automorphic group of S. Yeah, for a surface of general type. And here you can see that when G becomes large, when G is sufficient large, this number is almost equal to 4. So it's smaller than 20.5 times k squared. And also, we would like to mention that this bundle, the bundle for the fiber surface case is are also sharp. That is, we can construct an example to show that this bundle was sharp. Yeah. Here we also like to remark that in the fiber surface case, if the base QC is at least 2, then it is easy to get an upbound for this automorphic, for this abelian subgroup. That this is because, as we said before, that this GF can be decomposed into 2 parts. One part is an abelian subgroup of a general fiber, and the other part is an abelian subgroup of the base curve. Yeah, the general fiber is of genus at least 2. And if moreover the base curve is also of genus at least 2, then it is easy to get an upbound. But when the base curve is P1 and or an elliptic curve, it is not easy to get such a upbound. Here, our result is when the base curve C is the project line, and if the base curve is the elliptic curve, as far as we know, there is no general method. Okay. Here, this 3 example shows that this upbound are sharp. The first example is that we can, for NG, for NG is at least 2, we can construct a fiber ratio, and this fiber ratio this fiber ratio is from a surface S to P1, and it omits an abelian subgroup which is equal to this number, equal to this maximum number is 2g plus 1 square of this times kf square. And also we can construct 2 examples to show that the first upbound is also sharp. That is, for any G, we can construct a fiber ratio, and this and there exists an abelian subgroup which is equal the first number and larger than the second number. And also we can construct an example such that there exists abelian subgroup which is equal to the second number and larger than the first number. So our result on this fiber surface are also sharp. Okay. So okay. Finally, I would like to talk about the main idea of the proof. So first of all, for this first theorem, there are 2 main steps. So step 1 is we will get some bound from G1 or G fixed pencil on S. So here we should we introduce the G1 or G fixed pencil. So if G is an abelian subgroup, and a pencil is called G invariant if this subgroup keep this pencil invariant, that is for any sigma in G. Here sigma is an element any element from G. So if sigma maps lambda to lambda, this is called G invariant, and G fixed just means that it maps every member to itself. So G fixed is must be G invariant. Yeah, it's this requirement is stronger. And if we have a G-invariant pencil on S, we can blow up the possible base points and then take the Stern factorization. We will get a G1 fibration. I mean, blow up the base point and take this the Stern factorization. We will get a fibration on S theta. And because this pencil is G invariant, so if you blow up the base point, this group G can be lifted to the S theta, and such that after this lift, this G can be valued as a subgroup in this automorphic group of F theta. Yeah. So from G1 pencil or a G fixed pencil, we will get a G invariant fibration, and so that we can use our theorem B. That is this for any surface we get a G invariant pencil. So then our theorem B can help us. This is the the math result from we get from a G1 pencil or G fixed pencil. So suppose there exists a G1 pencil or G fixed pencil such that this pencil admit a small caloric degree. Here we say the caloric degree, that is the Ks times A is smaller than 1/2, the half of this Ks square, then we get this up bound. And also if Ks square is smaller than this number, and we have another some assumptions, then we can also get this up bound. And also if we start from a G fixed pencil, then we will also get our up bound. Yeah, this is just from these two lemma are based on theorem B, as you can see here. And here this one. Here GF for this in the theorem B, we have an up bound of GF is bounded from above by this number. This is almost yeah, this is if G is large, this is almost 4 times Kf square, and Kf square is just Ks square plus 8 times G. And here, if this caloric degree is not too large, then this the genus G is will be not too large, and then this Ks square plus 8 times G is almost a linear function in Ks square. And here, if G is large, this is almost 2, and this together will get on this the up bound with 20.5 times Ks square plus 100. Yeah. Yeah, if G is small, then of course, when G is equal to 2, this is the largest possible. Yeah. Okay, this is these two lemma, of course, are based on theorem B. And the second step improve the on Foster theorem is how to construct such a G invariant or G fixed pencils. Yeah, here is just if we have such a G invariant pencil or such a G fixed pencil, then we can use our theorem B to get the up bound, the required up bound. But how to construct such a G invariant or G fixed pencil? This for this step, we just consider this induced action on the globe section of this caloric divider, the pluricaloric divider. So the group G has an induced action on this globe section of pluricaloric divider. Yeah, because our group G is linear, so this action can be diagonalized. So this space admits a basis which consists of semi-invariant vectors. That is, for any element from G, the action of this G on this base is diagram, that is sigma act on this each Vi is equal to some chi I times Vi. This chi I is some character of this group G. Yeah, and yeah, and if you take two such semi-invariant vector Vi and Vj, then we will get a G-invariant pencil. Yeah. G-invariant pencil in this in NKS, and of course, if these two characters are equal, then this pencil is G-fixed. Okay, but to make use of this two lemma here, for G-invariant pencil, we should find a pencil whose caloric divisor is smaller than this two numbers. So we cannot just take two semi-invariant from this from this space, because for general two elements here, its caloric divisor should be here Ks times a member A in this pencil should be equal to n times Ks squared. So it does not satisfy this assumption here. So we should do move here. So the first step is that by our second lemma here, if we have a G-fixed pencil with this Ks square is not too large, then we have this bound for improve of this CNA. So by this lemma, we can assume that for any equal to 1, 2, 3, this induced action has max number of distinct characters. That is, I mean, this space should admit a base, and this base, this character here should be distinct. That is, if any two semi-invariant vectors have the same character, then they are linear dependent. Yeah, because if you take two semi-invariant here and their character is the same, then this pencil is G-fixed. And if we have such a G-fixed pencil, then we will get the bound we require. Yeah. Then we consider the multiplication map from this the symmetrical product of this globe section of the caloric divided to this globe section of this two Ks. Yeah. Then we have the following lemma to help us to find the required G-invariant pencil. This is a base of this H naught of Ks consists of semi-invariant vectors, and suppose that the induced action on this space has max number of distinct characters. Yeah, by our lemma 2, we can make such assumption. Then we will get either this map is injective. Yeah, if this map is injective, then of course we have this inequality, because the dimension of this space is just PG times PG plus 1/2. This is the dimension of the first space. And the dimension of the second space can be computed by Riemann-Roch theorems. This is the Ks square plus Chi-OS. Yeah, either this map is injective. Or if this rho is not injective, then we must have such a relation, that is, there exist two such four such semi-invariant vectors such that V1 times V2 and V3 times V4, they should be linear dependent. Yeah. Then we will, from this equality, we have such a relation for the corresponding divisors. That is D1 plus D2 equal to D3 plus D4, which is linear equivalent to 2 times Ks. And then we just taking the moving part of the pencil generated by either D1 D3 or D1, D4, then this pencil should satisfy this equality, because here is the equality for two divisors. So either half of D1 is contained in D3 or half of D1 is contained in D4. So either D1, D4 has some, I mean, they have some the moving part of this D1, D3 should be small. I mean, their fixed part is large, or the fixed part of D1, D4 is large. Then the moving part of D1, D4 is smaller, because this is the equality for two divide, not linear equivalent. This is just the equality. So by considering such multiplication map, we can get what we required in this in lemma 1. Yeah, and then if we have this equality, either we have this we get a linear a pencil we required, or this multiplication map rho is injective, and in this case we have this equality. Yeah, from this equality we can get that PG cannot be large. Yeah, because we have the Miyake-Yau inequality. This KS square is smaller than 9 times KOS. This is about 10 times KOS. So it is about 10 times PG. And here is PG square. So PG can, yeah. So PG cannot be large. So if PG is large, then we must live in this part. So we will get what we need. Yeah. And also for the, if PG is not, I mean, PG is small but is larger than 6, we can consider more the second multiplication map, and we will get what we need. Yeah, either this rho theta is injective, and we will get a similar inequality that this is injective, so the dimension of this space is less than the dimension of this space, and we will get the upper bound on this PG. Yeah, a similar inequality as this in this case. So, or we will get this rho theta is not injective. We will get a G1 pencil satisfy on requirement in this in lemma 1. Yeah, and then we will get we will prove on theorem A. Yeah, this is the main idea of proof for the first theorem, and for the second theorem here. The second theorem is a result for the fiber surface. So here we just require, I mean, here S F admits at least 3 single fiber, and S can be of I mean S is not listener of a general type. And to prove this result, here first we observe that we have an exact sequence as the following. So as before, here K is the subgroup which I mean K is the subgroup which keep every fiber invariant. So K can be valued as a subgroup in the automorphic group of I mean, and so K can be valued as an abelian group of the general fiber, and Q can be valued as an abelian group of the base curve. Because on base curve is P1, so this Q is either isomorphic to this Z2 times Z2, or the Q should be cyclic. This is because the base Q P1, there are only 2 types of abelian subgroup. Yeah, and if Q is the first case, then the size of Q is equal to 4, is bounded, and we can get easily this upbound. So the general case is that when this Cauchy group Q is cyclical. So when this Q is cyclical, then just that I mean the group Q has exactly 2 fixed points, yeah, on this P1. So to prove this theorem B on fourth step is the base change technical. So if the group Q has is cyclic, so it is locally it just like maps T to Kc times T, and then we can do some base change. This is a base change which is nullified over this two fixed point of this two fixed point of Q. Yeah, Q has 2 fixed point on the on P1. So this base change is nullified just on this 2 fixed point. I just write this 2 fixed point is 0 and infinity. And then we can do such a base change. And after this base change, one can lift this automorphic group G on S to an automorphic group G prime on S prime. Yeah, and on this S prime, we will get an abelian automorphism, which is just the extension of G prime, but is just the extension of G by this G model dz. Here is just the base changes of degree D. So we will get use this base change. We can get a new surface, and on this new fiber surface, we still have such an abelian automorphic group, and also for the second step, we can compute the Chen numbers of this base change, and this is okay. Use these formulas, we will get that on our new surface here, on our new surface S prime, there exists an abelian automorphic group G prime of size is equal to D times the size of G, and for the invariance of the new vibrations, we have this equality. So after this base change, we can reduce the problem to this new vibration. And this can help us a lot. For example, we can assume S prime is of general type. And also, for example, we can assume that F prime has sufficiently many single fibers, because F has at least 3 single fibers. So there must be, at least 1 single fiber not over 1 and infinity. So on S prime, there will be sufficiently many single fibers. And the final step is just that we, instead of consider the total Cauchy space, we just consider the middle Cauchy. We have an exact sequence. We will not consider the total Cauchy, S Cauchy G. We just consider the middle Cauchy. We just Cauchy this subgroup K. And if we consider this middle Cauchy, we will still have a vibration. This Cauchy still has a fiber over this base P1, and we will we consider this middle Cauchy, and then we will decompose this computation in several cases by here X is just the desynchronization, and this here sigma is just the contraction of X to some relative minimum model. Here Y is the new vibration over P1, and based on this the property of Y, we will get finally what we need here. Okay, sorry, the time is. I just explain to one word here. Because here G is an abelian automorphic group on this S, and K is a normal subgroup. So the Q, the Cauchy group Q admits an action on this Cauchy space. And after this blow up, the action of Q, I mean the coach group Q can be lifted to X, and then here we can choose some we can choose a good contraction so that the coach group Q can be reduced to an abelian group on Y. So the coach group Q can act on this group Y, and then in the finally if we want to find this to find some good some good divisor D in the branch locus, we can use this the branch locus on Y is Q invariant, and then this will help us to get this bound we required. Okay, I'm sorry here. I should stop here.
Okay, thank you. Any question or remark? No, I have a question. You did you take a base change from G to G prime. How do you show that G prime is abelian?
I mean here the first we just here this the coach group G Q here is abelian, so we can lift this abelian group to P1 here. So this should be abelian, and then we take this this extension, and we can write explicitly the action of this G prime on this product. Yeah. On this product, we can write down explicitly the action of this G prime. I mean, we can write down the explicitly.
I see.
And from this expression, we can see that G prime is abelian.
I see. So how do you choose this D, the degree of D? Is it multiplication?
D is here D is not crucial here, but we just take D is in our proof. We just take D is sufficiently divisible so that after base change, the fiber over over 0 and infinity is same stable. Then it is enough for us. I mean, we take D is sufficient divisible so that the new fiber ratio has same stable fiber over 0 and infinity.
Okay, thanks.
Thank you.
So any questions? Okay, so so maybe one more question. You say that if the equality is true, then you have a genus 2 fibration, right? Is it?
Yes. Here, if you mean the equality in theorem, the first theorem, this one.
Yeah, and then so this genus 2 fibration is unique.
Yes, because here we assume that the geometry genus is at least 6, and then K square is equal to this number, so it is at least 8. Yeah, so this fibration, so this fibration is unique.
I see. Okay. So you can recover the group action, you know, by looking at the action on the fibration, maybe.
Yes, because this fibration is unique, so any automorphism should keep this fibration invariant.
Is it from this a multiple canonical divisor? The fibration is from Kx or 2Kx something?
Pardon?
The genus 2 fibration is coming from the canonical divisor. Or?
Yes. Okay. This surface is on this knot line.
Like a Horikawa surface, I don't know.
Yes.
Any question? So if not, let's thank the speaker. Yeah.
Thank you.
Yeah. Okay. Today is yeah. So that's all for today. So we will see in 2 weeks time, right? Thanks, Liu Xing, for the talk. Okay. So yeah. Okay. So see you.